So for this next video, we're going to talk about Newton's laws. And I know everyone already knows these from physics, so we're not going to go into too much detail, but I do think it's important to just refresh everyone on them since they are covered in the first chapter of your text. So important thing to know about Newton's three laws of motion, we'll talk about his law of gravity in a second, is that they're all empirically validated, meaning that you can take data and show that they're true. They're applicable, and we'll talk about this more in dynamics for those of you that continue on with us into the spring, when you're actually observing the motion of a particle or a body in what's known as an inertial or non-accelerating reference frame. So don't worry about that too much now, because we're not going to be talking about things that are moving at all. I think there might be like one or two examples in the class where you actually have something at constant velocity, but yeah, pretty every so often we will see that, but typically the bodies that we deal with will actually be stationary. So Newton's first law is just the law of inertia that just basically says if there's no resultant force acting on a body, we'll formally define what that is in a minute, that whatever the velocity of the particle is, it's going to remain unchanged. And I'm using the term particle here. I'm sorry about it. I think it's because we're going to start with particle models in this class, but body in general. So if all the forces that are acting upon a body basically cancel each other out, we'll say there's no resultant force in that case. And whatever the velocity of the actual body was, it's going to stay that way. So if it was zero, it will stay at zero, which means the body is not moving. Or if it was moving, it will continue to move on at constant velocity. And you actually call oftentimes the mass of a body a property of its inertia. And we'll look at why that is in a minute. So if you do have a resultant force acting on a body, so we would know in that case that the acceleration, which is, again is just the time rate of change of the velocity, or the first derivative of the velocity, is going to be inversely proportional to the mass of the object. So the mass is just a quantity that describes how much inertia it has. For a given loading, how much will the actual motion change in that situation? So if you want to see what's going on, do feel free to look at down on the lower left here. We notice that this ball here, it's moving at some velocity, and the three forces vectorially, we'll talk about how to formally add those in chapter 2, but they all cancel each other out. So in that case, even though there are forces acting on it, the resultant force is zero. So that velocity will remain unchanged. In this case, figure B here was what we just talked about, Newton's second law. There is no force to cancel out this single force that's applied. So what that's going to tend to do is speed it up. If it's moving at some velocity, it's going to speed up. It's going to accelerate in that same direction. And the reason that it will accelerate in that same direction is, remember that both force and acceleration are vector quantities. So really, these have to be in the same direction. Since mass is just a scalar, it can change the length of that vector, but it's not going to redirect it at all. And Newton's third law is that of action and reaction, which just basically says if two objects are in contact and interact with one another, if object A exerts a force on object B, the force that object B exerts on A must be equal and opposite. And that's what that's showing you down there. And those are often called reaction pairs. So after Newton actually developed those three laws of motion, he developed the law of gravity as well. And what that says is that if just by this property of mass that bodies have, they tend to attract one another. And that level of attraction is proportional to their mass, and it's inversely proportional to the square of the distance between them. Now you might ask, well, I have mass, so does my computer. Why are we attracted? Why are we flying at each other? Why isn't that gravitational force accelerating me towards the screen? And the reason is that in general, gravitation is a relatively weak force. This constant of proportionality here is on the order of 10 to the negative 12. So really the only time that we're going to observe any phenomena of gravity in practice is when one of these two masses is incredibly large. And that, of course, is the case of the gravitational force that we're most familiar with, which is the attraction of all the bodies around us to the Earth. For those of you that have taken the second university physics course, you might look at this formula and say, hey, that looks a lot like Coulomb's law, only instead of m's, which describe mass, it's charges of body. It's still an inverse square law. But the big difference between Coulomb's law and the law of gravity is electrostatics is a much stronger force. But the reason that you don't observe it isn't that this scaling function is small in that case. It's that most objects are net neutral. Remember, when you're dealing with Coulomb's law and these are charges at the top, it's the net charge, or the sum of all the pluses and minuses. And under the majority of circumstances, unless we've transferred a lot of static electricity to ourselves by physically rubbing up against something, and for every plus we have inside us, we'll have a minus as well, so we're net neutral. In terms of weight, when you actually have an object interacting with the Earth and we're describing that gravitational force, symbolically, we can just swap out one of the m's the masses of the two objects for m sub b. So little m here is just the mass of the object that we're considering. Big M sub b is just the mass of the Earth. And what this is going to tell us is the gravitational force that the Earth exerts on any object. So in order to actually quantify what R is in this case, that would be, and we really haven't defined this idea of center of gravity yet, but just for now, for all practical purposes, assume that the Earth is perfectly spherical. So there's a symmetrical point right there at its center. We would have to measure the distance from the center of the Earth to the physical location of the object. And if you think about how big the Earth is, right, that radius of that sphere, if we're modeling it as a sphere, is going to be much larger than any little incremental fluctuations in height we might have on the surface of the Earth. So what that's going to mean is, for all practical purposes, when we're talking about the gravitational force that the Earth exerts on a body when it's on the surface of the Earth, this is basically going to just be about constant, because this R, even though it's technically the radius of the Earth plus whatever height it is elevated on the Earth, that the radius of the Earth is going to dominate that term. In a similar fashion here, of course, when we talk about the mass of the Earth multiplied by the mass of whatever object it is, regardless of how big we are, the mass of the Earth is much larger. So what that allows us to say is that we can actually approximate, and I'm just doing some setting these two equations equal to one another. You notice this is Newton's second law. This is Newton's law of gravitation. If you cancel the common factor of m, what that tells you is that any body that has a gravitational force exerted on it by the Earth, it experiences this acceleration, which technically takes on this form, big G, big ME over R squared. But since R squared is practically constant for most reasonable elevations above the surface of the Earth, we actually approximate this acceleration as constant. And that's just your G value that you hear as 9.8 meters per second squared. Of course, it is a vector, and notice that we're representing the direction of this vector by this unit vector, r hat. We'll talk about more what that is in a minute. But in Newton's law, that vector is always going to be drawn between the center of masses, and we haven't technically defined that yet, between the two objects. So when I'm here, wherever my center of mass is, my gravitational force is directed from there down towards the surface of the Earth. So we'll actually see that's called a normal force to the local surface of the Earth. So in terms of computing the weight of an object, it is a vector, and you can always take and just scale the gravitational vector G, which can be approximated for all practical purposes, is about 10 meters per second squared. If you want a physical interpretation of that, think about it. If you have a body and you drop it, each second, its velocity will increase in the downward direction by 9.8 meters a second. So if it starts at rest, a second later, it's about a 10, a second later, it's about a 20, and so on. It is accelerating there in free fall. Going back to our example of the wheel of the train on the actual track, we're told to assume that it's let's read this carefully, that the concentrated force exerted by the rail on the wheel, that's this white arrow, is 500 pounds. Describe the force exerted by the wheel on the rail and justify your answer with a physical law. So if you look at that, it sounds like I'm saying the same thing. But here, the white arrow is the force that the rail exerts on the wheel. We want the force that the wheel exerts on the rail. Well, remember, by Newton's third law, this is just an action-reaction pair. So what that means is if the rail pushes up with a 500-pound force on the wheel must push down with a 500-pound force on the rail. So that's just Newton's third law. And assuming the wheel is stationary, are there any other forces acting on it? Well, think if you just took the wheel and you held it out here by itself. We know the rail is pushing it up at 500 pounds. By Newton's second law, if there were no other forces acting upon it, that wheel would be accelerating in the upward direction. So it must turn out that there's some other force acting on that body that cancels out, from a vector perspective, the 500-pound force that the rail is exerting on the wheel. And that's likely, in this case, its weight, which is actually pushing it down. But since those two forces cancel each other out, we say there's no unbalanced force or no resultant force on the body, so it's just going to stay stationary. So that justification of the second bullet point there is Newton's second law. And the first bullet point is justified by Newton's third law. So hopefully that was a good refresher of Newton's laws for you, and I'll see you in the next video.